If one had to identify one idea as central and novel to reinforcement learning, it would undoubtedly be temporal difference learning. And that's coming from Richard Sutton and Andrew Barto, some of the pioneers of modern reinforcement learning. So yes, I think this is worthy of a video. In fact, this is part 4 of my 6-part series on RL fundamentals. My approach will be to present temporal difference learning and the related algorithms of Q-Learning, Sarsa, and expected Sarsa as the result of making a series of adjustments starting from Monte Carlo methods, which we're already familiar with. The hope is to compress the subject so we can understand a lot in a short amount of time. And I do mean a lot. Among other things, we'll do a careful walkthrough of the mechanics, understand and compare performance, and get down to the fine-grained actions the algorithms take in different circumstances. If you're trying to understand RL, this will be a pretty efficient use of your time. So, in the spirit of that efficiency, let's get started. Now, normally I do a review of the earlier videos, but there's just too much. Parts 1 to 3 altogether is a little over an hour, which is the equivalent of, and I did the math, 73,000 Wikipedia articles. You just can't summarize that. So instead of a review, I'm going to just say, watch the previous videos, or at least watch the video right before this one. Otherwise, you'll be completely lost. So from this moment, I'll assume you've done that. Okay, now, as mentioned, my strategy is to propose temporal difference learning as an adjusted version of Monte Carlo. Specifically, the plain, on-policy, constant alpha MC algorithm we covered in the last video. If you recall, which you better, almost all RL algorithms fall within the generalized policy iteration paradigm, where there are 2 components: policy evaluation, where we learn the value function of a fixed policy, and policy improvement, where we use the policy's value function to create a slightly improved policy. Now, the adjustment we'll make sits entirely within evaluation. That means we can study a Markov reward process, which is essentially a Markov decision process without actions. Also, we may reference state values instead of action values, knowing that these evaluation methods can be applied to both. If that doesn't make sense to you, I think you know what to do. Okay, the adjustment addresses a disabling feature of Monte Carlo. That is, an episode must complete before values can be updated. And that's a problem. If episodes are long, learning can be really slow. That's because the transitions and rewards within an episode contain useful information, which MC delays learning from. If we could learn from those, that would change our policy within an episode, which would change, and likely improve, how we explore that episode. This changes the algorithm's behavior to something that's often more efficient than MC. So addressing this is important, but I should note, we'll see the adjustment has other effects beyond merely fixing this issue. Now, to visualize the adjustment to evaluation, I'll use a simple Markov reward process. We have 4 possible states, S1, 2, 3, and T, where S capital T is a terminal state. The possible rewards are the integers from -3 to 3, and there's no discounting. And just like in Monte Carlo, we don't get to know the distribution function. From here, we can visualize our sequence of states over time with this grid, and our rewards with this. Let me explain. I'll walk through an episode. For time t equals 0, we sample our first state, which happens to be S3. And then, with a distribution that depends on that state, we sample a pair of a reward and the next state. Then we do this again and again until the end of the episode. The reason I'm representing things this way is it makes sums of rewards clear. Each one of these horizontal lines indicates the reward accumulated so far in the episode. That makes it easy to picture the returns. For example, the return G3. It's just the difference between the levels at t is equal to 3 and the end of the episode. Next, let's remember our goal in evaluation. It's to estimate the value of each state, which we do with a table. We refer to that with a capital V. Now, what happens in constant alpha MC is we sample an episode to completion, then we'll apply this update rule for each time step of every episode. Let's see that for a few more episodes. Now let's get into the temporal difference method. Let's say we just sampled this episode and we'd like to apply the update for the state at t equals 2. As mentioned, The issue with MC is that we need to observe until the end of the episode. So let's compromise that a bit. Let's say we just had to make do with only observing up until 4 steps after t is equal to 2, meaning we don't see the rewards beyond that point. The number of steps is an algorithmic input, so we call it more generally n. This means we need to update this in the update rule since it's only known at the end of the episode. We need to replace it with something. Well, we've observed some portion of the return, so we should certainly use that. The question is, what do we use in place of the unobserved part? Well, these things add up to G6, so we need something to approximate that. Wait a minute, that's exactly what our value function does. We can use the value of the last observed state as an approximation to G6. Here, the value is 0, but during the algorithm, it'll do the trick. And now we can see the TD method in action. Though, you'll have to forgive me, it's tricky to show the adjusted return like I did for MC a second ago on screen, so I'll leave that out. But outside of that, this is what it looks like to process a single episode. Notice how the value updates are applied within episode and are lagged by 4 steps. And obviously, this process repeats. Very fortunately, just like in MC, we ultimately converge to the right answer. Okay, let's now review this more generally. It's called n-step temporal difference learning, and it's easiest to understand if we recall the Monte Carlo approach, where we used this update rule for evaluation. To be clear, this refers to the state at time t of the nth episode. Now, in this rule, we call this the target. It's what we move our estimate towards on each step. In n-step TD, we replace the target with this, which is the sum of discounted rewards between t and t plus n, plus our existing value estimate to approximate the remaining rewards, discounted by n steps. The reason we do this is because that's what's observable at time t plus n. Also, things are appropriately set to 0 when t plus n is beyond the end of the episode. Now let's talk about n. As mentioned, it sets the lag between the time of the state whose value is being updated and the time of the most recent observation. And it's worth emphasizing, just like alpha, n must be specified up front before you run the algorithm. If you set this integer to 1, the algorithm is very eager to make updates. Values are updated after each individual reward. If n is infinite, then TD is identical to MC, since the delay is always greater than the episode length. Also, some terminology. Using a value estimate in the target is called bootstrapping. As we'll see, bootstrapping has major implications. So let's see that by comparing its performance to MC on a pure evaluation task. That is, the random walk example from the previous video. To refresh, it's a Markov reward process with 7 states, 2 of which are terminal. All rewards are 0 except when transitioning to the upper terminal state, in which case it's 1. Also, no discounting. The initial state will always be the center, and each transition is a 50-50 chance of going up or down. So one episode looks like this. As a reminder, when doing evaluation, the goal is to estimate the expected return from each state. Like last time, we can show the true values like this. Our algorithms begin by initializing estimates at 1/2, and we can measure performance using the absolute difference between our estimates and the true values. To keep track over time, we'll plot the average absolute difference over the number of episodes processed. To demonstrate, I'll run Monte Carlo with alpha equal to 0.03, which looks like this. Hopefully, this is nothing new. Okay, now we can see TD. I'm going to use an alpha of 0.1 and an n of 1, which gives us this. It looks like TD does a better job, certainly in the short term. But this isn't a complete comparison. The randomness of a single run and the specific choices of alpha and n make this view a bit too specific. So let's try something different. I'll use the same plot of error versus episodes, but this time I'll include sliders for MC's alpha and TD's alpha and for TD's n steps. But keep in mind, n is an integer. Here I'm starting it at n equals 4. A few other changes. Instead of using 7 states, I'll use 11. This will allow us to investigate a larger range of n's. Also, instead of running the algorithms just once, I'll run them 200 times, which will give a whole distribution of performance. For instance, this is the performance of MC, where the line gives the performance averaged over all 200 runs, and the band is plus minus 1 standard deviation. And now for the punchline. This is what TD's performance looks like. Not only does it do better faster, but it has a tighter, more certain distribution of performance. At least for these choices of alpha and n, TD performs better and is less risky. Now let's move around MC's alpha. As we can see, and as we already expected, over a certain range, a higher alpha makes for better early performance, but makes performance quite noisy in the end. Let's freeze this at an alpha that performs well. Now for TD. The first thing to recognize is that if we set n to a very high value and change alpha to be the same as MC's, TD is identical to MC. So TD includes MC as an option. But if we set n to 1, then we could do a lot better by increasing alpha. This is because a small n reduces the variance in the updates, so you can afford to take larger steps. Okay, now just to get a feel for the space of behaviors, I'll cycle through a few n's and for each, vary the alphas. Hopefully this gives you a sense of how performance can change as we vary these knobs. And if you'd like to explore this more, I've linked a code in the description you can use to play with this. There you can find a more fleshed out discussion of these two algorithms from this angle. But now, let's try a more direct perspective for viewing TD's trade-off between n and alpha. What we'll look at is the average error after 10 episodes. What I mean is this. Here, we have alpha along the horizontal axis and n along the vertical axis on a log scale. Using colors, I'll show the average error after processing the 10th episode. For example, this is what errors look like for n equals 8. I've normalized the errors to have a value of 1 when they have achieved their best value for a particular n, and that's colored as blue. That means around here, we achieved the best performance for n equals 8. Now, if we do that for the remaining values of n, we get the full picture. Clearly, for lower values of n, best performance is achieved for higher values of alpha. So we see there's an interdependence between n and alpha for achieving good performance. Still, observing performance like this doesn't explain why they perform differently. Sutton and Barto's book has a very interesting way of explaining it. The argument goes like this. We'll compare MC to one-step TD, and we'll adjust their algorithms slightly by using batch training. I won't go into the details, but the important thing is a fixed batch of episodes are processed repeatedly by each algorithm until their estimates stop changing. One reason this makes for a better comparison is because the final estimates arrived at do not depend on alpha, as long as alpha is sufficiently small. And here's the interesting thing. MC and TD arrive at different estimates, and their criteria for those estimates are different. It turns out MC's criteria is to minimize the mean squared error over the data, which is a known property of taking an average, while TD's criteria is to maximize the likelihood of the Markov reward process, the thing that we are assuming generated our data. I'll spell that out a little bit more. The Markov reward process is defined by a distribution P. It gives the probability of the next state a reward from the current state. Now, a very natural model-based approach would be to estimate P directly by counting transitions. That is, we form our estimate for the probability as the count of transitions from one state to the next state and reward divided by the count of visits to the starting state. This is the simplest version of maximum likelihood estimation for a discrete distribution. From here, we can use this to estimate the expected return from any given state. Now here's the cool thing. This is equivalent to one-step batch TD. Without actually doing this approach, batch TD arrives at the same answer. Not sure about you, but I thought this was pretty unexpected. And it's a nice way to conceptualize TD. So with that explained, I can state the punchline. TD's criteria is better for predicting returns. My impression is, it's because TD more directly uses the assumptions of the MRP. When we use TD, it's as though we are directly modeling the data generating process. MC, on the other hand, is just an averaging of the returns from each state, which doesn't reference the MRP. And that, in fact, has its advantages. MC is more robust to violations of the Markov property, but that robustness comes at the cost of doing less well when those assumptions do in fact hold. And one last detail. We can understand the non-batch version of TD and MC as roughly moving in the direction of what their respective batch versions would do. So that's the argument. Okay, that's a lot. If you've watched from the first video and you've made it this far, this has required a lot of focus. So pat yourself on the back and give yourself a 2 to 3 second break. Great, let's keep going. Now we're getting into the full-fledged algorithms. Algorithms that do the whole of generalized policy iteration. That is, policy evaluation and policy improvement. To start, we will discuss on-policy TD control, what is called n-step Sarsa. As a reminder, because this is a form of model-free control, we need to apply our algorithms to action values, not state values. If you don't understand why, you clicked on the wrong video. Now the first step is to redefine the return, like this. The change here is that the rewards beyond n steps in the future are approximated with an action value, not a state value, like we saw earlier. This means our update rule is slightly adjusted to this. This is just the update rule we covered at MC control in the last video, except we've changed the return. In fact, it's most efficient to understand TD control as just some modifications from the MC control algorithm we covered, which, to remind you, looks like this. And I'm not walking through this beast again. Now, the main differences from MC control are we changed the return definition, as we mentioned, and the update rule is applied during each episode and with a delay of n steps, as we covered at the start of the video. There's a bit more subtlety than that since we're interweaving value updates and taking actions, but that is the level of detail I will ignore. So that leaves a burning question. Why do we call this Sarsa? Well, it comes from one-step Sarsa. In that case, every update application operates on some tuple of S, A, R, S, A. Sarsa. Okay, but naming aside, an important question to ask is, what's the advantage of having n greater than 1? After all, my comparison of TD to MC seems to suggest TD is better and increasing n just makes the algorithm more like MC. Well, there certainly is a reason, and that's why the best n is problem dependent. To see this, let's imagine a grid where we start here. This is a deterministic environment where we have 4 available actions, up, down, left, or right, as long as the action wouldn't move the state beyond a wall. Our goal is to get here where the episode ends. All transitions into the goal state yield a reward of 1, and all other transitions yield a reward of 0, and gamma will be 0.95 to encourage the agent to get to the goal state quickly. So that's the game, get to the goal state. Now let's use 8-step TD and observe the first episode. We just blindly bounce around until we hit the goal state. But here's the important thing. Let's ask, which action values get updated following this first episode? Well, it would be the 8 transitions that immediately preceded hitting the goal state. Now this becomes an advantage on our second run because we are a lot more likely to stumble upon action values we've previously updated than the actual goal state. Once we're there, we're very likely, though not guaranteed, to follow the path to the goal state. This will create for another set of updates which help learning in the next episode. As you can imagine, if we run this many times, we'll eventually uncover the optimal strategy. So what's the advantage of a larger n? A larger n means we learn more from a single episode. And that quickly changes how we search the space, and that often makes learning more efficient. But again, as we saw earlier, a larger n means noisier updates, so it's a trade-off. Okay, at this point, we're in a really convenient position to learn 2 other algorithms. The first is Q-Learning. To understand this, I'll pose it as an adjustment from one-step TD control. It's easy to extend it to n steps, the notation is just heavier. Okay, so the primary adjustment is to the target. In one-step TD, the target is this. Remember, the target is what estimates are moved towards on each update. Now in Q-Learning, the target gets changed to this. What's happening here is, instead of using the action value of the upcoming state action pair to approximate the future rewards, we are using the max action value over all actions in the next state. And that, in fact, makes this an off-policy method. That's because the max operator is the presumption of a different policy, one in which we select actions by taking the max action value. that policy could in fact be different from the policy generating the data. That could be, for example, an epsilon greedy policy. And this has an important and subtle implication. It means that while we are taking actions according to whatever our behavior policy is, we are directly targeting the problem's optimal action value function. That's different from on-policy MC control, where we are approximating the optimal policy with the best behavior policy we end with. And also, relative to one-step TD, there's a change to the update's timing. To see that, let's write out a sample trajectory for some episode M. In one-step TD, we update the Q table here, which follows the completion of each Sarsa tuple. For one-step Q-Learning, we make the updates here. The updates happen before the T+1 action because that action isn't part of the update rule. The maxing action takes its place. And that does it for Q-Learning. We'll see how it performs in a minute. For now, we're on to expected Sarsa. Confusingly, this is an adjustment to the one-step Q-Learning algorithm, not Sarsa. The adjustment is to change the target to this. What we have here is our next step action values weighted by our policy's action probabilities. As we'll see, using an average instead of relying on sampled values, as we would in Sarsa, has the advantage of being less noisy, at the cost of a more expensive computation. And one last detail. As presented, this is an on-policy method, but it's very easy to make it off-policy. If the policy we use in the target is not equal to the policy generating the data, we'd have an off-policy method. Easy enough. And finally, we can do some examples. For Sarsa, Q-Learning, and expected Sarsa, we'll look at their performance on two examples. In these comparisons, we'll only cover the one-step case, because that's the version I just showed, and otherwise, it would be a very heavy lift visually. The first example is called cliff walking. For animation purposes, my version is a little different from Sutton and Barto's. Okay, as is typical, it involves a grid where we start here and want to get here, which ends the episode. We have actions like these available to us, which deterministically shift the state to the neighboring state. And this is the cliff. If the agent moves into it, they get a reward of -100 and the episode ends. Otherwise, all transitions yield a reward of -1, and there's no discounting. So we'd like to get to the goal state as fast as possible while avoiding the cliff. In fact, this is the optimal path. Now for all episodes, we'll be using an epsilon of 0.1 and an alpha of 0.5. We'll be keeping score here where the horizontal axis is M, the number of episodes processed, and the vertical axis is the sum of rewards, which is G0. So when we run Sarsa for the first time, we get a pretty terrible sum of rewards. But we'll get better. Let's try again, and again, and again, and again. In fact, let's just do it many more times. After we've done so, this is what a typical episode looks like. Now to evaluate the algorithm, we should rerun it, say, 400 times. In that case, the average sum of rewards looks like this. Naturally, we can also plot Q-Learning, which is quite a bit worse. So what's happening? It comes down to this. In the typical case, Sarsa is executing this path, whereas Q-Learning is executing this, which, due to the epsilon chance of exploration, is rather costly to travel along. To understand this, let's recall their targets. What we see is Sarsa's update uses the next step action it actually takes, which is sometimes an exploratory action. Therefore, it's estimating returns for the policy that includes epsilon exploration. And because of that, it knows that going near the edge is costly, and so avoids it. However, Q-Learning is doing something different. The target has this max operator, which means the Q table isn't estimating the policy used to generate the data. Rather, it's estimating the policy defined as taking the max action value, which is very similar to the policy generate the data, except it doesn't include epsilon exploration. So it doesn't in fact think the edge is costly. That cost is due only to epsilon exploration. In fact, if we set epsilon to 0 at the end, Q-Learning would execute the optimal path. Now let's see expected Sarsa, which has this performance. And its most typical path at the end is this. Basically, expected Sarsa on a per episode basis is a more efficient version of Sarsa. Again, it can be understood by the difference in targets. For Sarsa, we know that this action comes from the policy distribution. In expected Sarsa, we are just using that distribution directly to calculate the expected next action value. In other words, What Sarsa does with sampling, expected Sarsa does with an expected value, and that eliminates one source of sampling error, and makes the updates more accurate. Though it should be noted, the calculation of the target is more expensive for expected Sarsa since it involves a weighted sum. Let's do one more example, this time one that isn't deterministic. This one is called Windy GridWorld, and again, my version is slightly different from the books. Again, it's based on a grid where we start here and we want to get here with the typical actions. However, now we have some wind blowing up. These numbers tell us how much our next move is shifted up. For example, if this is the state and the action is to go right, then this number says the next state will be one position above the state pointed to, which is here. Let's also add some randomness. If the wind is non-zero, then we will shock its value by -1, 0, or 1, each with equal probability. That means if the agent selects go right repeatedly, that would look something like this. Okay, now I'll show you the algorithm's average performance over 1,000 episodes. This is Sarsa, this is Q-Learning, and this is expected Sarsa. One thing that's clear is that Q-Learning learns the fastest. In the long run, it looks like expected Sarsa and Q-Learning are about the same, and Sarsa is slightly worse than both. All right, I'm not sure what explains this difference. Maybe it'll help to consider one run of each algorithm and inspect the paths they took after a certain number of episodes. So this is the first path taken by Sarsa, this is the first one taken by Q-Learning, and this is the first one taken by expected Sarsa. All right, we obviously need to see more than that. Over here, I'll show how many episodes have been processed. Now here goes. Okay, that was cool to see and shows you how these algorithms bumble around to find the right answer. But it didn't explain their difference in performance. For that, I don't have much of an answer. It makes sense that expected Sarsa is better than Sarsa in the long run since it reduces a source of noise. Q-Learning maybe is more aggressive in pursuing strategies that might be optimal, leading it to more quickly go rightward. I'm really not sure. But I guess I shouldn't be surprised there's no obvious theory as to why one algorithm is always better than the other. If that was true, the runt algorithm wouldn't be used, but we know they're all used. The best one really must be problem dependent. And I think this is a typical experience in RL. You see some performance differences on multiple algorithms, and it's very hard to attach a story as to what explains that difference. It's just a really hard problem. Speaking of problems, you have one. You understand reinforcement learning only up until the tabular case. The case where all possible states can be listed discretely in a table, but the real world is much more complicated than that. For that extreme challenge, you'll need to understand function approximation. If only there was a video explaining that topic.